To wrap up chapter 11 here, we're going to use our model for estimation and prediction, and then we're going to assess the values here. So 2 tasks we want to accomplish. We want to be able to estimate the mean value of y, that is the expected value of y for any given x, and then we want to predict an individual y for a given x. So the accuracies in our estimated mean and our predicted value are going to be measured by sampling errors here of the least squares line when it's used as an estimator and as a predictor respectively. So we need to be able to analyze those sampling errors. So the sampling errors for the estimation of the mean of y and the predictor for an individual new value of y, well, that standard deviation of the sampling distribution of the estimator y hat of the mean value at a particular x value, we'll call it x sub p, p stands for particular, is given by sigma sub y hat, so that's standard deviation of the estimator y hat, is sigma times the square root of 1 over n, and your sample size, plus xp minus x bar squared over sum of squares of xx, where sigma here is the standard deviation of epsilon, your error. So not the standard deviation of the whole population, but standard deviation of your random error epsilon. We call sigma y hat the standard error of y hat. And then the standard deviation of the prediction error, so this is standard deviation of the sampling distribution for the estimator y hat, and this is standard deviation of the prediction error. And we're doing that for the predictor y hat of an individual value y at a specific value x, which we would call xp, like we did up here. So we denote that sigma y minus y hat. So that's the deviation, the error, prediction error, is again sigma, that's the standard deviation of the random error epsilon. And then the only difference inside the square root here is we've got a plus 1 out in front. So the standard error of prediction is always greater than the standard deviation of the sampling distribution. Now note that we'll use S to approximate sigma when sigma is unknown. And that was the S that we had computed previously. So then with these two errors, if we wanted to do a 101 minus alpha % confidence interval for the mean value of y at some specific x equal xp, we would take our point estimate, y hat, plus t alpha over 2 times the estimate for the standard error of y hat. So that standard error estimate is this guy right here, except we'll be using S. So that's y hat plus or minus t alpha over 2, and then we're just plugging in this here, but with an S instead of sigma. And then t alpha over 2 is based on n minus 2 degrees of freedom. And then the prediction interval, so this is confidence interval for the mean. This is the 101 minus alpha % prediction interval for an individual y value at x equal xp, is again y hat plus or minus t alpha over 2 times the estimated standard error of prediction, which is this guy here, but we won't know sigma, so we'll substitute S. So y hat plus or minus our t alpha over 2 S, and square root 1 plus 1 over n plus xp minus x bar squared over SSXX. Again, n minus 2 degrees of freedom. So let's put this to work. Let's compute some intervals for example 1. Again, this is the medication dose versus the headache pain. So here's our model, sum of squares of xx, our x bar, and then our S. So we want to find the 95% confidence interval for the mean pain level, that's the mean y, at a dose of 500. So that is our x sub p. And then find the predicted value for pain. Again, that's our y. Confidence interval for mean pain. That's our mean y. And the 95% confidence interval for that value. So again, our XP here is 500. We're doing 95% confidence, so our alpha is 0.05. And so our T alpha over 2, half of 0.05 is 0.025. That's the right area. So the left area, 0.975. So we do inverse T of 0.975, comma 2. And we've done that one previously. That's 4.30. And then our y hat value to go with XP is 500. So we're taking our y hat here, plugging in 500. So 500 goes in there. And I don't know if you remember, we did this one before. It was 4.12. And actually, it's 4.173 if you want 3 decimal places. And so our first interval, our 95% confidence interval for the mean pain will be our y hat value, 4.173 plus or minus 4.30 square root 1 over n is equal to 4 plus our XP is 500 minus our x bar 375. That gets squared. We're dividing by sum of squares of xx, 287, 500. So it's this 4.173 plus or minus. Let's compute this, our standard error. So that is going to be 4.3 times, and we'll do alpha y, no, I'm sorry, that's not what we want. We want square root here. So square root of 1 over n, so that's 1/4, 0.25, plus, and now we do our alpha y equal nr. In the numerator, we have 500 minus 375. Close our parentheses, square it. Denominator 287, 500. So 2.372. So 4.173 minus 2.372, 1.801 is our lower limit. And let's go ahead and second enter, and we'll change that minus to a plus. 6.545. So we're 95% confident that the true mean pain level is in this, for 500 milligrams of medication dosage, is in this interval. So it's between 1.8 and 6.5. And then same thing down here, except we've got a 1 out in front. So this will be 4.173 plus or minus, and let's go ahead and compute that. So I'm going to come up here, do second enter, and then I just need to insert a 1 as 1 plus 1/4. So that'll be 1.25. Or if you want, 1 plus 0.25. And everything else is the same. I'll use 4.3 instead of 303. So 4.911. So 4.173 minus 4.911, negative 0.738. And then we add it instead of subtracting. 9.084. So we are 95% confident that our predicted value for pain is going to be between negative 0.7 and 9.08 when you have 500 milligrams of medication dosage. This is a pretty wide margin here. That's really not giving us a lot of useful information there. And then just to caution here, our least squares prediction equation should be used to estimate the mean value of y or the prediction only for values of x that are inside the sample data range here. So our 500 was inside the sample data range of 100 to 800. If you use values outside that range, you could get very large errors in your estimation or prediction. So your least squares model will provide a poor representation of the true model when your values are outside of too far outside that data range. And unfortunately, the TI-84 does not have a built-in function to do your confidence interval for the mean and confidence interval for the predicted value.